Well, I'd like to also thank Barbara and Claude for the invitation to speak today. This has been an extremely stimulating workshop in a very historic place. What I want to talk about today is sort of a petrologist perspective on some of the dynamical considerations for the behavior of the lithosphere and its connection to the asthenosphere. And as you'll see, I'm really going to be just focusing on one property, and that's density. And I think you'll all understand very quickly, or know already, anticipate why that's so important. Collaborators involved in this work, Derek Schutt, I've collaborated with him, and that's been a very fruitful sort of collaboration between petrology and geophysics. Art Brown is a student of mine who is now postdocing in Aarhus, and Mike Baker, experimental petrologist, very much like myself, and we've been sort of puzzling over how to parameterize, especially the subsolidus phase relations for peridotite. And Kenny Peterson, who is a numerical modeler that has gotten involved in this as we're trying to incorporate some of the petrology into the dynamics. Well, we've seen this slide umpteen times here. I just want to reiterate what's been said time and time again, in that we have very stable regions here, cratons cored by very old lithosphere, and we know that it's seismically very fast, and it's interpreted as being cold to great depths. And it can be surrounded then by younger Proterozoic and Phanerozoic mobile belts. We've also seen this picture time and time again, and I don't need to spend a lot of time on it, but there are lots of ideas here, and these are sort of three of them summarized by Cinti Lee on how you generate this material that makes up the continental lithosphere. And of course, we have the plume origin here, where you have very high degrees of partial melting, leaving these residues that are melt depleted and buoyant. This idea that you have underthrusting imbrication of oceanic lithosphere here, and that's one way of collecting together depleted lithospheric material, but you also have oceanic crust involved, which would then turn to eclogite. So you've got to remove some of that if you want this thing to be buoyant. And then the third one, of course, is through arc magnetism and the depleted material associated with the passage of fluids and partial melting in the wedge environment over time. Well, just to remind us that, in fact, in the real world, we are melting something that might look like this, which is a garnet lherzolite here. It might have a density, at least at room pressure and temperature, about 3.4. And when we do the melting, we're going to be producing a melt that will crystallize to a basalt, and leaving a residue that might wind up being something like this, that is depleted in the components that you're making up the basalt, largely iron and aluminum, which are very important agents which are controlling effectively the availability of luminous phases or lack of that in your residues. And the important thing is the density under these circumstances is not conserved. And you can see here that both the residue and the basalt have lower densities than the protolith that you started with. And of course, that's a thankful thing, because in fact, if it were not for that, then the oceanic lithosphere would sink a heck of a lot faster than it does. And so, to some extent, that's a good thing. But of course, if we then push this basaltic material back down, we can recover some of that density deficit here if we transform it to eclogite, basically producing lymphocytic pyroxenes and garnet. So to sort of think about these density relationships, of course, in the real world, we need to sort of think about, especially in the continental lithosphere situation, the evolution of these residues that are left behind from melting. Again, this is just for review. But of course, the process by which you generate these residues is by polybaric decompression melting. And so you're all familiar with one or any number of cartoons here. This one's from Langmuir and Forsyth. With the corner flow, sort of two-dimensional corner flow situation here, I just want to draw attention here to the residual melting column over here. So as that material passes through the melting regime and moves laterally, you're basically leaving a lithosphere that has been partially melted. The melt has been extracted to form the crust, and there's some variable degree of melt depletion associated with that. And if you intersect the solidus at some shallow level here, you might get up to, at the top of the melting column, the residual mantle might be melted by, say, 15%, while if you start much deeper here, you might, at the very top of that melting column, melt it as much as 40%. And that's all, of course, a function of the potential temperature of the mantle and which path you're taking. Now, the path you're taking here, we're not showing anything about the mineralogy as we go, and that's really where we have to draw on experimental petrology. Mike Walter is here, and so I put in this very classic phase diagram that now I just got 25 years ago, if you can believe it, when this was published. But I want to sort of make a point here is that really there's been a lot of experimental work done on the melting of peridotites, but Mike's work on studying peridotite was perhaps and still is one of the most thorough studies over a broad range of pressures where all of the phase chemistry or compositions were analyzed and the melt fractions were known, the modal proportions, the mass balance was done and convincingly such that this is a set of sort of benchmarks experiments in which we can try to understand what these residues look like. So those two melting paths, 1600 degree potential temperature, or maybe say 1380 potential temperature here comes up, and it's just very easy for you to see that a path here of decompression melting along this hot potential temperature here will sort of pass through these stability fields. As you're continuing to melt, you're leaving residues that are more and more refractory here, and of course a lower temperature decompression path intersects the solidus much shallower, and the phase relations associated with that through the melt depletion are going to be very different at the same pressures. The important point here is that to generate highly melt-depleted lithologies, they have to be occurring at relatively shallow levels. Okay, well, there's this idea of this isopycnic hypothesis that Tom Jordan introduced actually before 1988, but this figure is from that paper here. And it's just this notion here that the negative sort of thermal buoyancy of this cold subcontinental lithospheric mantle is balanced somehow by some change in the composition of that mantle. And so that leads to this isopycnic equation right here. And so what you have to do here is basically sort of balance the effects in just sort of a back of the envelope or very simple relationship here. If we assume a volume thermal expansivity of 5 times 10 to the minus 5, then effectively if you have a 200 degree temperature difference between the oceanic adiabat and some continental geotherm here, that would require a density decrease by however you want to do that in that residual mantle of 1%. Okay, so that's just sort of a number that you can, now that will change depending on what you use for the thermal expansion and various other things, but that's sort of a ballpark. Now, if we look at this in terms of density relations, and then, in fact, we could imagine that we have some fertile mantle adiabat here on the left here. That's with a potential temperature of 1320. I'm just using this as an example. And if you were to then allow that fertile mantle material to cool down to some continental geotherm that would have a surface heat flux of 40 milliwatts per meter squared, its density relations would be over on this, reflected by this right-hand curve here. And so there's this density difference here. So if you want this to be isopycnic, to have the same density, then you have to have some mechanism by which you deplete this material such that you bring its density in accordance with the fertile mantle adiabat. So another sort of back of the envelope is that if you want to get a 1% density change through some process of melting, you can get, for an 8% depletion, you can get a 1% density change. So what that means here is that at this level, right, this lower level right here, you're going to, that's associated here with a 1.5% density change here, and that would require melting of on the order of 12%. And up here, a 3% change in density here, say 24%. Now, that's rather reasonable when you think about the melt productivity, and that we're talking about, say, 10 or so percent melting per GPa, about 1 per kilobar during decompression. So that's certainly a feasible process during adiabatic decompression melting. One of the problems, though, is that at these kind of depths here, it implies that you're intersecting the solidus at very great depths. So you've got a very hot, high potential temperature, a very hot upwelling mantle. Okay, so a number of years ago, we sort of went through to these kind of calculations and trying, and I'll explain more about how we're doing these, but we were trying to take into account the real mineralogy of peridotite and the effects of melt depletion on those. And so here's your fertile adiabatic mantle. That's the isopycnic situation that you want to aspire to. Here would be this fertile mantle and along that cratonic geotherm. And I'm just showing you two other examples. If you were to melt a pyrolite mantle at 3.5 GPa by 20%, this is a real rock that you're melting, but by 20% at 3.5 GPa, and then determine what its density relations would be along that continental geotherm. We'd have this curve here, and then this one to the left here would be 20% melting if you were to melt that lithology at 1%. So this is just to give you a sense here that, in fact, to do that, of course, you're starting out way over here somewhere if you're at temperatures just at near the ridge axis where you're actually forming this material and it's still hot. But as it cools down, what you can clearly see here is that, in fact, at some point here, that material is basically becoming denser than the fertile mantle adiabat. That's isopycnic situation. So really anything right here at this crossover, anything above that is going to basically be negatively buoyant. And that's sort of an inescapable conclusion here. So somewhere there's sort of some density crossover here, and such that if you're sort of assuming these kinds of lithologies, there's no way that you're able to maintain the isopycnicity across the full depth range here, and the upper part becomes too dense due to the thermal effects of cooling, and the lower parts can remain positively buoyant. And that crossover here for these examples here is going to be somewhere, say, 140 to 165 kilometers. So we went through this sort of exercise here and developed this plot. It's perhaps a little confusing, but the main point here is just simply this white line, dashed line right through here, which is the line of neutral buoyancy. That's the intersection between the mantle adiabatic, the isopycnic situation, and whether or not the mantle, due to partial melting here, is negatively buoyant, or below that is positively buoyant. And this is plotted as a function of the surface heat flow. So as the surface heat flow decreases along that, for that geotherm, then effectively you're intersecting that neutral buoyancy at greater and greater depths here. Okay, so if you do this and you sort of then try to compare it to some xenolith suites here, this is just an example from the Tanzania craton here. This is the data is from Sinti Lee and Berta Rudnick. Here's the geotherm that they would propose here, 50 to 52 milliwatts per meter square here for those xenoliths. And if we then take into account these effects of melt depletion, here you can see their contours. There's our fertile mantle, but there's 10, 20, and 30% melt depletion. Here you can see that in fact for their geotherm, which is, or somewhere between there, coming through here, that these xenoliths right here, at least the majority of these, and granted there aren't a lot of them here, but are actually lying below this isopycnic line right here. So they're positively buoyant with respect to that reference situation. And in fact, if you look at places like Kapfal, you see the same kind of picture that when you go through this exercise, that the xenoliths, the garnet leurzolites, are all lying in that region below the isopycnic line for that particular, for the geotherm that would be appropriate for that craton. Okay, so it's not isopycnic in the sense, but in these particular cases, it's actually positively buoyant. Okay, the approach, the standard approach that's been taken by Jordan, and it was followed up by Sin-T Lee, was in fact to try to have some way based on the composition of the xenoliths to make some estimate about their densities. And what's done here is that they're all referenced to room temperature and pressure here. And so this is a plot of the bulk density of xenoliths as a function of the bulk mg number of those xenoliths. And there are two calibrations. This is the older calibration of Jordan, and this was Sin-T's revised calibration just using garnet peridotite xenoliths. And there's a point that I'd like to just draw attention to out of his paper. He says that the pressure and temperature derivatives of the compositional end members of peridotitic minerals are very similar, and therefore the compositional derivatives of the elastic moduli with respect to mg number at room temperature and pressure conditions are applicable at elevated pressures and temperatures. And that may not be a totally unreasonable conclusion or assumption to make here, but you can see that there's a great deal of scatter or variability in these xenolith suites. And if you try to draw a best fit line through here, the R-square values are pretty small here. They're very far from a good correlation here. And he shows this range of 2 sigma on here, which is considerable given the resolution that you want to have in these the densities of these. Now, one of the things that when you look at that range here, if you were to take the experimental data that we have and we were to then take, say, 6 or 3 GPa data and go through and back calculate what the STP densities would be for those, you would have a trend up here for the 6 GPa and down here for the 3 GPa. And so effectively, this full range here could be accounted for just by different melting scenarios or histories for those various xenoliths, and not really just a random uncertainty propagated through in terms of the bulk density. So one of the problems, of course, in this is that just using this simple mg number index to try to calculate densities could be rather misleading. And really, we're talking about this range right here, both the 2 sigma that Sin-T and the difference here between the 6 and 3 GPa is about a 1% range, which if we go back to the other, is like a 2% or 200 degree difference in temperature or an 8% difference in melt depletion. And those are quite significant in terms of when we're trying to model the density relations within the continental lithosphere. One other point here, and I can go very quickly through this because of Mikhail's talk in the previous session here, but this is plotting mg number bulk or olivine versus the modal proportion of olivine. And these are Mike Walter's experiments here. I just put those on here. So if you start with sort of a pyrolytic composition right here and you melt it at 7 GPa, you'll have a trajectory off in this direction, and at lower pressures you can see that the slopes decrease here. And so it's quite easy to get from these kind of compositions over here through melt depletion up and account for, say, some of the xenoliths or the xenoliths that we find perhaps beneath the Greenland craton. But you can see here that they're xenolith suites here with a Phanerozoic here, and that's sort of following and tracking the abyssal peridotite trends here. Proterozoic here, things start to sort of trend out to lower modal olivine, and then we've got this big field here for the Archean, Harzbergites, and Lürzelites. And I just want to point out that that's largely dominated by the Kapfel suites in this compilation here. And I just want to drive this home, but it was done very nicely earlier. Certainly in the Kapfel case, largely what we're looking at, this is a work that we did just a few years ago. We were basically trying to get at what the effects of the various compositional trends in these xenolith suites and how they might affect seismic velocities, to sort of tease that out. But what we did here was just a principal component analysis of the Kapfel xenoliths here, and this just shows the variance reduction for the three principal components here: the mg number effect, which we associated with melt depletion, this OPX enrichment effect, which we associate sort of with some kind of metasomatic process, and then there's also a small effect due to garnet and CPX enrichment, which may be related to some kind of melt infiltration. But the dominant effect here in the Kapfel is this OPX enrichment or silica enrichment trend, which is associated with metasomatism. So to get back to this, one of the problems with just using mg number to calculate density, of course, is that when you get into the Kapfel suite, that in fact for very similar mg numbers, you have a very different modal mineralogy, and that's going to greatly affect the density relations that you're calculating. So you need to have a much more sophisticated way to calculate these densities. So one of the things that we can do now is, we can calculate what the composition and the modal mineralogy is of a peridotite along its solidus. One of the tricks is that we are following some thermal history, some cooling, and we have to understand the subsolidus phase relations in these systems, and that is a bit more challenging. And one of the things we also have an interest in doing is making this as simple as possible so that it can be integrated into numerical models. With Mike Baker, we try to develop a very comprehensive parameterization of the subsolidus phase relations based on all of the available high-quality experimental data that we could get our hands on. And so this calibration here is based on 57, at least this was several years ago, 57,100 experiments ranging from 600 to almost 2,500 degrees C, 1 atmosphere up to 10 GPa. And basically what we're doing here is that we're basically coming up with exchange coefficient, distribution coefficients that are a function of temperature, pressure, and composition, and then using mass balance and the stoichiometry to basically solve here for the mineralogy as well as the phase compositions as a function of temperature, pressure. So it's just a very simple calculator that allows you to do this, but it's calibrated on the actual real experiments, and so we have a great deal of confidence that it's at least able to reproduce the experimental observations. Our densities are calculated. We did sort of a similar kind of thing, and trying to make this as simple as possible to be used in numerical routines. And this is from the work we did a number of years ago, the Schutt and Lesher paper. So I just want to show you some comparisons here between the subsolidus mode calculator that we have. And this, as an example, this was not included in our calibration here. This was more recent work by Mark Hirschman's group here that was melting KLB1. They had determined the near solidus composition, modal mineralogy, and phase chemistry for the melting of this peridotite at 3 GPa. And so there are a bunch of one-to-one lines right here. And the squares here are our calibration for the melt calculator here. You can see they do a very good job following that one-to-one line. And then I make 3 other comparisons here, basically 2 for the Perplex program and for P-melts. Both of them are thermodynamic databases, and in those thermodynamic databases, basically there is always this effort to to try to sort of minimize the free energy of the system here. And you oftentimes internally are very consistent, but sometimes things are not very accurate. And I think you can see that reflected here in the deviation in all these plots. You don't have to get specific, but in all these plots in terms of the composition of the phases here, as well as their modal proportions. But it's not so bad in the case of, okay, I'll go quickly. It's not so bad in the case of density here because these are all offsetting effects. So if your phase composition is a little different, your modal proportions are a little different. And in fact, I think all of these routines do a pretty good job of melt density. So the subsolidus phase relations from our calculi, I just want to show you one example here. This is why it's important to track these things. You can see here that if you take that this is MM3, this is a peridotite composition that's been used experimentally. But if you decrease temperature here, you can see that the olivine doesn't change much, but you can see that the proportion of clinopyroxene, orthopyroxene, garnet change considerably. And in fact, here at temperatures above maybe 1100 degrees or 1000 degrees here, that effectively orthopyroxene is on the left side of the reaction producing orthopyroxene garnet, and it switches over here. And that's, of course, all very much related to the nature of that solvus for the pyroxenes. But to get back to the issue of the density here, if you take account of the subsolidus reactions here, you get some insights into basically what effect that has compared to if you just were to consider the thermal expansion here. And so here's the solidus mineralogy here, and if you were just to take into account the cooling of it, you sort of have thermal contraction that would follow here, but if you now take into account the fact that there are changes in the phase proportions due to the subsolidus reequilibration of these lithologies, then in fact you can see it's much more enhanced. And so there it is, garnet. You can see garnet's controlling all of it. In the case of orthopyroxene here, in fact, the orthopyroxene density is actually lower in the real case than it would be just based on thermal expansion. So if you just look at the relative change relative to thermal expansion here, you can see that if you take into account the subsolidus evolution of these systems, that in fact you can get up to an order of a 1% increase, higher density change than you would have predicted if you just considered just the effect of thermal expansion. So that's important. Okay, so I'll just sort of end right here. What we wanted to do now is to sort of consider the polybaric evolution of a system. And so to do that, along the solidus, we are using p-melts to calculate what the bulk composition of the residue is along the solidus. And then based on that, we're using this subsolidus MOVE calculator to calculate the modal mineralogy and change in their compositions. And we are now bringing this into along various continental geotherms here, and as a function of time for a lithosphere that was formed, say, at 3.5, so 500 million years later here. There's 2 billion years and 1 billion years. We will go very quickly through here, but basically you can look at the effect of all of the different parameters on density here. And the bottom line, cut right to the chase, is that even for these natural cases for polybaric decompression melting here, that in fact all of these geotherms become negatively buoyant. So under any circumstance, under these conditions here, that in fact the upper part, at least above, say 120 to 150, probably even more way down in here, that all of that mantle lithosphere, that residual mantle lithosphere, is too dense. It's to be isopycnic. Okay, so that intersection is going to be way down at much greater depths. And it doesn't have a big effect on what you assume for the potential temperature of the asthenosphere. So that isopycnic condition just can't be met. So that's exactly what we concluded here in a very simplified way, where we weren't considering the effect of the subsolidus evolution and these mineral reactions. It just makes it a lot worse when we do take that into account. So the bottom line is that the mantle, when you're producing this depleted mantle, even this very highly depleted mantle in the shallow mantle becomes too dense at those levels. And if you want to bring it into an isopicnic situation or even get close to that, somehow you have to take that dense mantle and you've got to move it vertically down. And that seems to be absolutely essential here. And I think that's consistent with the observations of the xenoliths. The xenoliths are far too depleted at the depth from which they came to effectively be generated by any kind of a simple decompression melting scenario, even at extremely high potential temperatures. Okay, so in terms of the evolution of this thing, even if you take into account the subsolidus evolution, they're negatively buoyant at these kind of depths, and somehow you have to take this stuff that is formed at shallow levels at a high degree of depletion, and you've got to get it down deep. And so you look at these various scenarios here, and you ask yourself, is there a mechanism in these scenarios to, in fact, do that? And we can generate depleted lithosphere of various degrees of depletion, but in fact we don't have it at the right levels. It's being produced at rather shallow levels, or it's not depleted enough to become positively buoyant. And so I think that is an issue that we have to reconcile with, and so it doesn't help to put any dense material and have eclogite in there. That just makes it worse. It's just even more negatively buoyant. So if do I have 2 minutes? Okay. So now I think we've got we've got algorithms here that in a simple way can calculate the densities, and there are other ways we can do that, or other programs that can do that. But we also can calculate and track, I think, reliably the subsolidus evolution of the system. And so where we want to go is to integrate that into numerical schemes where we're keeping track in fine detail the effects of melt depletion in a dynamically upwelling and extending system here. And so this is just some of Kenny Peterson's, and this is very preliminary work. I just wanted to share this with you because the way we're going on this is that one thought that I've had certainly is that if we have to take this very depleted material that is too dense at shallow levels and get it down, we need some mechanism for vertical transport, efficient vertical transport. And so I'm referring to this as sort of a mini Wilson cycle where effectively we're extending and compressing and extending and compressing in these cratonic environments over time. And you'll see in this model just an attempt to try to simulate that situation here. So we're just opening and closing this, and what you can see here is the grayscale here, the darker. Whoops. Let me try to do that again. Just stop right there. The darker gray. Whoops. Aye. How did that? Whoop. Yeah, we'll just stay right there. But this darker, that's the most highly depleted material right here, melting zone. And every time that you basically open and close, you get some decompression melting, and you close it again, you have some way of perhaps vertically transporting the most depleted material down deep. And I think we may need something like that to basically redistribute this material within this evolving continental lithosphere to, in fact, sort of approach conditions that are near isopicnic or certainly give us the positive buoyancy that we need at depth to support the stiffer, dense material at shallow levels. Okay, I'll stop there.